So transformer phasor diagram we have discussed, and then phasor diagram related to only resistive. Okay, and now we are going to discuss the same phasor diagram again, but with inductive load. So the phasor diagram will be going to be repeat case. So then you will get the revision of the phasor diagram, and you will also get the another phasor diagram related to transformer. So you know already. I will again draw this diagram. Simple circuit for transformer. Okay, supply voltage V1, resistance R1, inductance L1 on primary side, back EMF E1 on primary side, back EMF E2 on secondary side, R2, L2, and remaining voltage V2. Okay, these things are clear. Okay, now how to draw the phasor diagram? The first we need to draw no load component, and then we will have to draw a loaded component. Here the load is I. Okay, R and L is a load. Alright, so the process for drawing the phasor diagram is very simple. First, we will draw a one horizontal line, and that horizontal line represents no load flux phi 0. Okay, and then we will have to draw the current vector I0. And that I0 is it has an angle, little bit angle with the phi 0. So here it is a magnetizing component IM, and here it is a working component IW. Up to here everyone clear? And working component has a phase angle phi. Okay. After that, what we have to do? We have to start from this side. We have to draw V2. Then we need to add 2 drops. Then we have to consider the current I2 dash. Then we have to draw the vector I1, and then we have to consider the vector losses in R1 and inductor. So here the current is I2, and here the current is I. Okay, and I1 vector current is addition of no load current plus secondary component, which is dash, because it is transferred in primary side, and working component already done with no load current already done with working component and magnetizing component. Okay. Alright, so where we have to draw the phasor diagram or phasor of the V2, we always draw the phasor of the V2 in this quadrant 1, 2, 3, third quadrant at some angle. Why is that so? Because after adding voltage in V2, voltage drop in V2, we have to get E2, because that the KVL equation on secondary side. See, supply voltage is there, that must equal to opposite side of the E1, because it is opposite, plus drop in resistor I1 plus drop in inductor I1 XL1. Okay, supply supply voltage must be same of the voltage even resistive drop, inductive drop. On secondary side, supply is E2. So E2 must be I2R2, I2XL2, and finally V2. These are the two KVL equations. Supply voltage is equals to voltage plus drop. Generated voltage is equals to voltage plus remaining voltage. These are available on remaining voltage. V2 is okay. So we have drawn V2. We have drawn no load condition. This is only this portion is a no load condition. No load current is there. Okay. Flux is there. Working component, magnetizing component. Then we will start from the V2. Now why we draw here a V2, that we will reveal after completion of the phasor diagram. Now the next step is to talk about current I2. Where should the current phasor I2? If resistive load is there, then see only this circuit. Then V2 and current flowing through this circuit, which is I2, are in phase because circuit is pure resistive. But if circuit is RL, then V2 and the current flowing through this circuit has some phase angle. And if it is inductive portion, then it is some degree lag to the supply voltage only in this portion. V2, I2 lags by the V2. So I draw I2 here somewhere. Okay, and that angle, let's call phi 2. Phi 2 is angle here. Here the angle is phi 0, let's call it. Okay, because it is on secondary side, so we give second number to the angle. Okay, so only consider this portion. V2, I2, and current is flowing in this way. So here current flowing is I2 and voltage is V2. So current is lag behind the V2 only in this portion. So it is lag behind. Up to now everyone clear? Why current lag behind the supply voltage? Okay. Now add this all those terms. In V2, here is a V2. I have to add I2 R2. For that I need I2. We have I2. So I will add I2 R2. For that I need to draw parallel line to the I2 and add into V2. So parallel line is something like this. And the vector I2 R2, let's say something like that. Okay. After that 90 degree. Inductive portion is there, so that counterclockwise I2 XL2. I will add such a way I2 XL2 so that V2, I2 R2, I2 XL2 will become E2 and that E2 comes on this line. So I have to extend that line approximately something like this. So this is the I2 XL2 and this one is E2. Okay. So now see the phasor diagram. E2 is equals to V2, I2 R2, I2 XL2. E2 is equals to V2, I2 R2, I2 XL2. Okay. This is the addition on secondary side. Now we need to come primary side. So for that I need I1. I1 comes from addition of I0 and I2 dash. I have I0, but I do not have I2 dash. But I2 dash comes from I2. We know that it is exactly equal and opposite, not equal but opposite. So somewhere here I2 dash will be there. And supply voltage is V1, transformer is step up. Okay, So secondary side voltage will step up, simultaneously secondary side current will step down. So that if secondary voltage is higher than the primary, then primary current will be higher than the secondary. So I2 dash must be higher than I2. So I will draw large vector compared to the I2 on primary side. So this is the large vector and opposite to the I2. So it is called I2 dash. Okay. Now I have I2 dash and I0. Okay. Previously there was one question that why E1 and E2 both are in this side, and then we will take E1 opposite to this side. So simply you can remember that whenever supply voltage is there, whenever flux is generated on this primary coil, the flux created by this coil is changing, then it will induce EMF inside itself. That is called back EMF. In the vicinity of that magnetic flux, if any other coils come, then according to same Faraday's law, inside this coil there will be also another induced EMF. And that EMF is also opposite to the supply voltage. So all the E1, E2, some third coil, E3, fourth coil, E4, fifth coil, all the coils are there different. And all the coils generate EMF. Then they all on one side and supply voltage is on one side. Supply voltage will go on this side, then all the E1, E2, E4, E5 all are opposite side. Okay. Why we flip this vector particularly? Because we need to take minus sign for set the KVL equation. We know that it is opposite, and it is opposite to the supply voltage. Here it is not opposite. Here V2 and E2 is not opposite. Here E2 generated after that V2 is the remaining voltage. It does not try to oppose it. Even try to oppose V1. So we need to put minus sign. And whenever you have opposite phasor, so one phasor is here, then opposite phasor is only 180 degrees. If I have one phasor here, and I say what is the opposite phasor of this, then it is in this direction. Minus V. If I have here a one phasor E, what is the opposite phasor here? Sorry, here. This is the opposite phasor. If I flip this phasor on this direction, then that will become minus E. If I flip this phasor on this direction, then it will become minus E. Okay. So E1 comes here and then we will flip 180 degrees, so that will become minus E. So now I have I2 dash, I0. So I2 dash is here, I0 is here, add them and get I1. So I will add by law of parallel logarithm. Parallel line from I0 to I2 dash, parallel line from I2 to I0. Okay, and that join both point together, we will get I1. So this is our vector I1. Now we will have I1. We know that this is step-up transformer. So let's say it is double, almost double the voltage. And E1 is the back EMF of the supply voltage. So we can say that E1 is always lesser than the E2. Because if this is the 100 volt, then this will be the 95 or 99 volt. And if it is step-up transformer, then almost 100 to double, 200 volt will be E2. So this vector is always lesser than this vector. E1 is always lesser than E2 step-up transformer. If the transformer is step-up. So E1 is here, but less amount of the E2. So that will be your E1. Okay. Let me draw very small. Alright. And then flip the vector and make the negative on E1. So I will create a negative vector of the E1 here. These two vectors are equal, negative E1. And now I have to add in negative E1, I1 R1. Where is the I1? I know where is the I1. So draw the parallel line to the I1. Okay, and make a vector which is I1 R1. Then perpendicular line in this direction. Okay, and then add I1 XL. XL inductor is there, so I have to go 90 degree counterclockwise. This is I1 X7, and then add I1 X7, I1 R1, negative E1. So negative E1, I1 R1, I1 X7, adding all together will give us V1. Okay, and this is the complete phasor diagram. If two vectors added together, then we will get I2, Z2. Only these two vectors. If these two vectors added together, then I will get I1Z impedance, and this is called impedance triangle. Okay, so you can see here, where is the river? Here is the river. These are the voltage loss triangle. These are the weak EMF. These are the primary side current. And what is the angle between V1 and I1? It is something what we call phi 1, from here to here. Now, this is not to scale phasor diagram. It is not perfectly according to the scale. Because see the vector V1, it is larger than V2. So it is not step-up transformer. But we make the drawing of phasor diagram in such a way that you can understand it in a better way. I0 has not this much amount of angle here. It is almost near to phi 0. So something like this. It is here. I0 will be here somewhere. And then we have to draw V2 somewhere here, like this one. And then here I2. And then we will add two vectors. So here it will be E2. And then there will be E1. And then I0. I0 will be I2 dash. I2, then I2 dash. Then I will add those toes. I will get I1. And then I will add here I1 R1. And here I2, I1 X1, and then I will add here V2. So V1 then becomes smaller than V2, almost. Or for that, these loss are small, then I have to make scaling. This is smaller and this is also smaller. Then it will become a scale diagram, almost near to scale. Okay. Then the vector V1 will be small than the V2. Otherwise, the vector here is larger than the V2, but that is quite okay. These are the general understanding steps to how to draw the phasor diagram. If you start the drawing of phasor diagram by considering I0 in this direction, phi 0 in this direction, then you have to draw perpendicular line here. Okay, then I0 here, V2, I2. Okay, add both. Here another vector. I1 add together, I2 dash I1, then E1, and here is the V. So your whole diagram will be shifted in this way. If you start to draw I0 in this way, then the whole structure is shifted in this direction. You can draw this diagram in this way also, then the whole structure will shift in this direction. So in generally we draw this line horizontally and this line perpendicular, even in E2. In this way we will start to draw the phasor diagram. Okay. So in your syllabus, only half of the portion phasor diagram is considered, but we cover all the complete portion. So previous was resistive. For that, I2 will come with in phase V2, and then you have to follow all the steps. Then RL come, then I2 is lagged behind by the V2. If capacitive comes, then this I2 will go here because it is leading. So it will be leading here, and then you will have to follow the steps. Okay. Capacitive we are not going to discuss right now, but this is called the RE load. Okay. So here the phasor diagram for the transformer on RE load. Okay. So if they ask to draw the phasor diagram, then you can draw this figure, equation 1, equation 2, and equation 3. Three equation, one drawing, and step of the phasor diagram. Clear? You can now draw the phasor diagram. Auto transformer. Now, what is the meaning of auto transformer? Suppose you have a single phase winding of a first transformer, and then because E1 already induced, here E1 already induced, I am going to draw that again, because again and again you see this drawing. Here I will have a primary winding, and here I will have a secondary winding. Okay, and back EMF E1 is already there. Supply voltage V1, back EMF E1, R1, L1. What we can do? We can remove insulation from this side, on this side of the turns. Okay, and we can attach here one pointer. This is the ground, let's say. And this voltmeter here with the ground. So these two things are connected. You can see that. These two things are connected. And if I change the position of this pointer, okay, then what this voltmeter will measure? It will measure the voltage between this point and 0. This is the ground, so it is 0. So that will measure the voltage between this point and that point. So we can say this is the primary and this term here up to there, it is secondary. We do not need this winding. We can use back EMF as a secondary voltage. So this is the idea behind the auto transformer, and the otherwise working will be the same. Like no load flux will be there. Okay, and all those things. Now, if I want to draw the equivalent diagram of this circuit, then it will look like this. That I will have here a primary winding, okay, and then I can take a one point out, let's say from here and from here. Then there will be the load connected here, and here is the voltage V2, and here is the supply voltage V1. This is the primary side, this is the secondary side. So if I want to mark it, then I will mark something like A, B, and C here. What are the turns on AB? That will be N1. What are the turns on BC? That will be called N2. And what are the remaining turns between AC? That will be N1 minus N2. N1 turns, remaining N2 turns, and N1 minus N2 are the final remaining turns. What is the current flowing in this winding? I1. The same current will flow here. Yes, I1 is there. And then current divided into the two paths. In general, ordinary transformer. This kind of the transformer is called ordinary transformer if there is a secondary winding is here. So secondary winding has a current I2. Then I will also has a current I2 here. from this junction or from this point, I1, from I1 current I2 will go in this direction, then downward side remaining current is I1 minus I2. Are you getting this point? I1 current is here, that will flow here. After that, I2 current will flow in this direction. Then what is the remaining current in this portion? I1 minus I2. If I want to represent current not in downward direction but in opposite direction, then minus of this I2 minus I2. Here, so if I want to draw the current which is flowing in downward direction, and that is I1 minus I2. But now I want to draw the current in upward direction, then it will be negative of this. And if I take a minus sign inside, then this will become plus I1 and that will become minus. So that will become I1 minus I2. Okay. So I will plot here. See, minus here. So I2 will be negative. Wait, I2 will be negative. Minus minus plus. I1 will be positive. So I1 will be positive. I2 will be negative. Right? I write down I1 first. Or you can say something like this: negative I2 minus minus plus I1. Then I will write down I1 first and then minus I2. Okay? So this is why we are doing this kind of thing, that we will see that why we do not keep I1 minus I2 in this direction. So in this direction is there. So I will write down I1 minus I2. Okay, so take a revisit. What we are doing the theory of auto transformer. In ordinary transformer, two windings are there. What we are doing, we do not use secondary winding. We will remove the insulation from this portion. Okay, so that portion will become conductive. Are you getting the point? If I have a winding something like this, okay, and if I will remove each and every turns insulation from this side, so that will become a copper color, copper connection, copper color, and this is also copper color, brown copper color. And now I will shift from here in this way, then this all things are conductive. Are you getting my point? આ બાજુથી આ બાજુ જઈએ તો આટલો પોર્શન જે છે હવે કંડક્ટિવ બન્યું છે, કારણ કે એટલું ઇન્સ્યુલેશન આપણે રિમૂવ કરી નાખ્યું છે. That kind of the portion insulation has been removed. Okay. Otherwise, insulation is there, and these open conductor are not touching each other, so it is not short circuited. Okay. Those portions are crossing each other. They have insulation. Only minor portion is there where we remove the insulation. So this portion will become a conductor. Okay. So here we have done it on each and every side. So that will become a conductive, and we attach here a voltmeter, or we can attach here a load also. Okay, load will be connected, and then something it is happening something like this, but it is not safe. We can say that it is an analogy. Suppose I have here a resistor, and resistor has a length, and it has a supply voltage. Okay, let's say supply voltage is V1. So some current flow in this direction. Let's say I1. And this resistor is I1 R1. So what is the voltage drawn across resistance I1 R1? And what is the amount exactly equal to V1? Because V1 voltage is already given to this resistor. But now if I take here a voltmeter, and if I connect here one wire and connect another wire here, then I shift this point. So if this point is here, then voltmeter will say voltage V1. Let's say 100 volt. Then I will shift the voltmeter point in this direction. Then it will only read the voltage between this portion and that portion. And that voltage is lesser than the full voltage. So here is 100 voltage, here is a 90, 50, 40, 30, 10, 0 volt. So in this way voltage divide into the resistor. Or we can also sometimes do not want to draw the continuous resistance, then we can divide it, something like that. One resistance, second, third, fourth, stepwise. So here full voltage, here some voltage reduced, remaining voltage appear across the voltmeter. Here another voltage reduced, here reduce, 0 voltage. Okay. So V1 is equals to voltage of this one plus 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 this one. So in this way you can change the voltmeter pointer and you can get the different voltage. And in electronic circuit that will happen. In some electronic circuit 3 voltage is needed and we give the 5 voltage, then they will put some resistor here, and that after that resistor they will take the tapping. From the tapping they will give another voltage to the other circuit. So here is the 5 volt, I want 3 volt, then I will connect between only this portion of the resistor and apply that to voltage to further circuit. So that will divide the voltage by resistor. It is called voltage divider, and there is a rule is also there, voltage divider rule. Same way parallel resistance are there, then there will be the current divider rule. Okay. But here inductive portion is there, and we divide the voltage per turns, EMF per turns, and we will collect the voltage of the remaining turns. So here what is the phenomena? Voltage drop occurs across the resistor and we collect it. What is here phenomena? Voltage induced across each turns and we collect it on secondary side. So this is the induced voltage collection and this is the drop voltage collection. Alright. So this is the idea behind the single phase auto transformer. And then what we have done, same I1 current flowing in this direction, let's say. Okay, we take the tapping, load is here. This portion called the term N1. Actually turns are same, it is not different. But which are the N2 turns? Those turns which have insulation removed. Those portion is only called N2. So here is the portion is called only N2. Because that is insulation removed turns. Okay. Or throughout material insulation has been removed, we can say. But whenever we put the point, N2 will change. If I shift the point upward, then N2 will be higher. If I shift the point downward, then N2 will be lower. So I1 is there, N1 turn here, N2 turn here, remaining turn N1 minus N2, current flow here. From some portion of the current I2 will flow in this direction, the remaining current I1 minus I2 flow in this direction, or opposite I1 minus I2 flow in this direction. Okay. Now, A, B and C portion is there. Voltage V2 is the available voltage to the load. Here voltage is not V2. Here voltage is the, let's say E2. But after that there will be the resistor and inductor. Here also there will be the resistor and inductor. Okay. And the basic theory behind this is that we can do all the performance, all the operation that ordinary transformer has to do, but with saving of copper, because here no external winding is there, and copper is costly. After gold, copper is very costly material, so we have to save the copper. For that we use only a one winding. So main purpose for this is to saving the copper. So for the saving of copper, we all know that on ordinary transformer, power on primary side must be same as power on secondary side. Okay. And power is primary side voltage and primary side current, and power on secondary side is secondary side voltage and secondary side current. And if I take V2 on this direction, on this side, then that will become V1 minus V2, and I1 on another side, then that will become I2 minus I1. and that is the transformation ratio 1 divided by K. It is standardly expected that K is V2 by V1. So you can write down here K is V2 by V1, I1 by I2, and another thing is M2 by M1. How this come? You can compare V2 by V1 and M2 by M1. Higher the turns, higher the voltage. So if turns ratio is high, according to that voltage ratio is high. So directly from the voltage ratio you can set the turn ratio, but current ratio you can set from the power equity. So this is the final equation for ordinary transformer, and this is called transformation ratio. K is called transformer ratio. If transformer ratio is 1, it will not increase the voltage. If transformer ratio is 2, that means V2 will be 2 times higher than V1. If transformer ratio is 10, okay, then V2 will be 10 times higher than V1. Simultaneously, current I1 will be 10 times smaller than the I2, because it is inversely proportional. If I put here 10, then equate 10 with V2 by V1. What will happen? 10 V1 is equals to V2. So V2 will be high. Now put 10 here and equate only these terms. Then I1 is equals to 10 I2. So I1 is 10 times high. Primary side is 10 times high. Here secondary voltage is 10 times high. So this is the transformation ratio. With the help of K, you can determine all these things. Now we are going to derive the equation for saving of the copper. For that, power delivered to the load. Now where is the load? Here is the load. And power, so that is the V2, I2, voltage and current. That is fixed. Next thing is, which is very important, the power in the winding AC. Where is the winding AC? Here. So power in winding AC, and we call it EAC, voltage across AC winding. So current flowing through that times the voltage. And what is the voltage across AC winding? What is the voltage across AC winding? Here across AB winding, V1. Collection from C point to B point to V2. And voltage add in the series. This whole winding is in series. So here is the voltage across AC plus voltage across CB is equal to V1. We know this is V2. So this one must be V1 minus V2. Okay. So I1 here V1 minus V2. And this is the power across this winding. Turns N1 minus N2, same way voltage V1 minus V2. After that, what is the power transferred? That is power in BC circuit. So that power transferred, that means power in BC winding. That is the power transferred. So whatever the power here, V1 I1, after that remaining power comes here. After that some loss occurs and another power used at this point. Another power across the AC has been lost, or it is not utilized, we can say. Okay. So power transfer. So from here to here, transfer power, that means power across the BC winding. So for that, what we have to do? Voltage across DC winding. What is the voltage across this winding? V2. Because we do not consider here resistor or inductor. So whatever the voltage here, same voltage will be here. V2. And what is the current here? I1 I1 minus I2. Okay, so power delivered to the load, here power V2 I2, here power in the winding AC is I1 V1 minus V2, and the power delivered, so from BC winding only V2 I1 minus I2. If I say what is the power supply, then it is V1 I1. Okay, it is not necessary, but let's write it down. Power supply, that is the, okay, wait a minute. Power in winding AC, do not write down E, that will make confusion, and this will create a V1 I1. So V1 I1 is here, power, and across the A load V2 I2, then across the winding AC I1 V1 minus V2, and across the winding BC V2 I1 minus I2. These are the four powers across different locations. Now we can do a little bit modification by using this transformation ratio, that is, take I2 as a common from this equation. So V2 I2, here I1 by I2 minus 1. V2 I2, I1 by I2 minus 1. Okay, here is one mistake. Here we will take current I2 minus I1 as it is. That is flowing in this direction, because this is for the representation. The current is flowing in this way. So I will draw both current I2 minus I1. Why will this change polarity? That will reflect here. I2 is 1 minus I1 by I2, and V2 I2 1 minus I1 by I2 is K. Okay, transformation ratio I1 by I2 is K. So here V2 I2 1 minus K. Okay. Now the ratio of power transfer to the power delivered. So ratio of power transferred to power delivered. What is the power transferred? This one, power transfer. Which winding is that? This winding. What is the power delivered across the load? Okay, so that ratio is this power V2 I2 1 minus K divided by what is the power here? V2 I2 power delivered V2 I2. So V2 I2 cancel and you will get 1 minus K. Okay, this is the ratio. This much amount of the power will deliver from this side to this side, from BC to the total. And what is the power conducted directly? So here is the power conducted directly. And that is the power delivered to the load minus power transferred by the transformer. So power delivered to the load is V2 I2 minus the power that is consumed. Power transferred by the transformer action, that means this one, minus power transferred. That is V2 I2 1 minus K. So power conducted directly, sum of the power delivered minus sum of the power transferred. So અહીંયા જે power એમાંથી આ પાવર બાદ કરી દઈએ છીએ આપણે, તો આપણને કેટલો પાવર કન્ડક્ટ થયો છે એના વિશેની માહિતી મળે છે. આમાંથી આપણો પાવર બાદ કરતા પાવર ડિલિવર્ડ ટુ ધ લોડ અને એમાંથી 1 માઇનસ k જેટલો પાવર ટ્રાન્સફર થાય છે, સબસ્ટ્રેક્ટ કરીએ છીએ. અહીંયા રેશિયો લઈએ છીએ એ બંનેનો, આ ક્વોન્ટિટી અને આ ક્વોન્ટિટી. There will be the ratio between these two quantity. Then you will get the percentage, and if you get subtraction, then you will get the exact amount that what is delivered. So if you do the mathematics, then V2I2 minus V2I2, that will cancel, and minus minus plus, that you will get only k times power output. Okay. V2I2 minus V2I2 minus minus plus V2I2k. So that will become k times V2I2. So this is the power conducted directly. So whatever the transformer ratio, according to that, some of the power will conducted in the winding and remaining power will be transferred. So what is the remaining power that available at the load V2I2, and what is the power that has been conducted inside this winding? It is k times the V2I2. So it is dependent on the transformation ratio. Now still hold on, I will give you the time to write it down, because once theory has been started, so we'll have to complete the whole theory. And now we are talking about the copper saving. Now, volume of the copper is proportional to number of tons times current flowing through it. Why is that so? Because if I have a wire here, alright, and this one is the cross section area of the wire, and this is the length. Okay, so cross section area will give me direct information about current, because higher the cross section area, then larger current it can carry. Okay, and length give me, or number of tons give me the idea about length. Okay, and volume is cross section area into length. Okay, area into length is the volume of the copper. So copper volume is area, cross section area into the length. Cross section area directly depend on the current, and length is depend on the tons. If I have a same radius tons and 10 tons are there, then I can directly measure the one periphery of a 1 ton, multiply with 10, so I will get the length. So if you have a number of tons and current, then indirectly by product of these two, you can get the volume of the copper. And volume of the copper is the weight of the copper, because you know the density of the copper. So this is volume or weight of the copper. Are you getting this phenomena or not? Or should I repeat it? If I have a wire, okay, what is the weight of the wire? What should I have to do? I have to get the knowledge of density. Density that means mass per unit volume. Okay, so density I know. What is the mass per unit volume? I have a on paper density. That copper material is fixed. I know the density. So if I want the amount of the weight of the copper, then what should I do? I have to take the volume. If I have a volume of the copper, then with the help of the density, I can take the weight of the copper. And how I will get the weight of the copper? Indirectly on the scale. So I will have a length, I will have a cross section area. So cross section area into length will give me the volume. If I have a volume and if I know the density, then I can easily get the weight of the copper. Okay, because density is equals to weight per unit volume. Okay, density is equal to weight per unit volume. You know the density because material is fixed, copper is there. You know the volume, yes, cross section area by turns. If I know the current, then I can definitely know that what is the cross section area. 5 ampere current is there, then I needed this millimeter diameter wire. Then it can sustain 5 ampere current, otherwise not. So if I know the current, I get the cross section area. If I know the turns, number of turns, then I will have diameter of the turns. Then I can get the radius of the turns. And if I know the radius, then I can know the 2 pi r. So I will get the length and then second, third, fourth, 5, 6, 7, 10. So 10 turns, so 10 multiplied by 2 pi r, then I will get the length of the wire. So length of the wire will come from the L. So AL is the volume, I can replace it by NI. N for the A and N for the area for the current and L for the turns. And if I know the volume and density, then I can get the weight. How heavy the copper is. So weight of the copper is directly taken by Ni. Clear? Everyone? Simple trigonometric triangular relations is there. So I will remove this. I hope you can understand it, okay? Volume of the copper is proportional to Ni. Now, in ordinary transformer, weight of copper is equals to N1 I1 plus N2 I2, right? Two windings are there, number of turns on primary winding and number of turns on primary winding, Ni. Secondary winding, number of turns, and current flowing through it. I can use this relation here, transformation relation. See here, N1 I1 is equals to same as N2 I2. N1 I1 is same as N2 I2. So I can write down here N1 I1. Here is also N1 I1. So there will be 2 times N1 I1. Okay. Multiplication will remain same. Then after, the top section AC, which has a turns N1 minus N2, and that will carry the current I1. See the top section AC that has a number of turns N1 minus N2, and that will carry the current I1. And bottom section BC has turns N2, and that will carry the current I2 minus N1. Okay. So the winding weight is proportional to these two quantity here and there. So in auto transformer, weight of the copper in this winding turns and current N1 minus N2 times I1 plus in this winding turns time current N2 I2 minus I1. Okay, so here is the N1 I1 minus N2 I1 plus N2 I2 and minus N2 I1. Anything that is same, check. N1 I1, N2 I2. Okay, so N1 minus N2 in bracket I1 plus N2 I2, that is correct, minus N2 I1, up to the correct. Now take N1 minus N2 as a common and the current I1 as a common plus N1 I1 and and then n2 I1 as it is. So what I will do, I will keep this as it is, n1 minus n2, here is I1, n2 I2 replace with n1 I1 from this condition. Okay, n1 I1 is equal to n2 I2 minus n2 I1. So what will happen from both sides? I can get n1 minus n2 common. Here n1 minus n2 common. I will take n1 minus n2 here also both common. So n1 minus n2 I1 minus here also n1 minus n2. And current is n1. Both current are n1. Okay, n1 minus n2. N1 minus n2, and then n1 minus n2 I1, here n2 I2, negative n2 I1. So this one term will remain as it is. Here will replace n2 I2 with n1 I1 minus n2 I1, n1 minus n2 common here. Some mistake is in here. Okay, correct. n1 minus n2 I1 is here. n2 I2 I1. Okay, so here it is a plus, then here it is also plus. Correct. So these two terms are same, so we can say 2 times n1 minus n2 I1. Let's check up to here. Go through this one and see what we can, if we have query, we can ask. In ordinary transformer, weight of the copper, primary side N1 I1, secondary side N2 I2, and add both weight together. Use the transformation ratio so that here you will get N2 I2 as N1 I1. That will become 2 times N1 I1. 2 times N1 I1 in ordinary transformer. In auto transformer, this is the current through this winding is different, current through this winding is different, turns are different, and here and turns are different also here. So what is the current I1 here into turns? So N1 minus N2 multiply with current here. Then current from this winding and turns I2, which is I2 minus I1. So I2 minus I1 is the current multiply with the turns. Make the simplification. You can, by the way, ignore these steps. You see here, don't look at this step. Only see here, N2 I2 minus N2 I1. This term as it is, N1 minus N2 I1. N2 I2 again replaced by N1 I1. This N2 I1 is as it is. અહીંયા સુધી clear છે? અને અહીંયાથી from here you can take I1 common, then there will be the N1 minus N2. So our term as it is a this term as it is N1 minus N2 I1. In this portion again take I1 common, then remaining term will be N1 minus N2. So these two things are same. N1 minus N2 I1, N1 minus N2 I1. So 2 times N1 minus N2 I1. Okay. And this is for the ordinary transformer. And now you can take the ratio of these two things. I have space, so I will complete with it now. See, ratio of auto transformer 2 N1 minus N2 I1, and ordinary transformer 2 N1 I1. So what will happen? Here N1 I1 they get cancelled, minus N2 I1 get cancelled, N2 by N1, 2 cancel, so that will remain 1 minus N2 by N1, which is K. So that is K. Okay. So this thing is called saving in copper winding. How? What is this numerator? Auto transformer copper. What is denominator? Ordinary transformer copper. Auto transformer copper is 1 minus K times ordinary transformer copper. If you will have 1:1 transformer, then ratio K will be 1. 1 minus 1, that will be 0. Copper saving is 0. So if you want to use auto transformer as 230 volt input and 230 volt output, then 2 winding transformer is the benefit. Let's say you use step down transformer, and that step down transformer, that means ratio is what? 1/2 K. Here is the K, N2 1/2 and 1/1. So ratio 1/2. K 1/2. 1 minus 1/2, 1/2. Auto transformer is 1/2 of ordinary transformer. Copper winding in auto transformer is only needed 1/2 on that ordinary transformer. So this is the saving. So if you will have a better step down transformer, then copper will be saved more and more in auto transformer rather than ordinary transformer. If you want to use in a step up or 1:1 transformer, then 2 winding transformer will be beneficial. If step down transformer is there, then this kind of thing transformer is beneficial. So in laboratory we will have variac, and that variac is only used for the purpose of step down transformer. So if you want to use step down transformer, avoid this kind of transformer, take this kind of transformer. So you will have changed the turns and correct the output. So only with the one winding, you will have all the operation that performed by the step down core transformer, ordinary transformer. Okay. So when they ask you the theory about copper saving in auto transformer, okay, or auto transformer, just auto transformer, then you have to write down this one drawing. This is for step down. Reverse the figure. Give the supply voltage here, load here, V1, V2, okay, then that will become step up auto transformer. After that, mention transformation ratio, power, 4 points are the power. Supply power V1 I1, another power V2 I2, power across this winding, power across that winding. And then try to derive the equation of power transferred and power delivered. One is a ratio output to input, another is output minus input, up to that. If they ask you the theory that how much copper saving in auto transformer, draw the drawings, okay, mention the power or 4 powers, and start copper saving by volume or weight of the copper is proportional to NI. This is the key thing. NI. How does this come? Copper volume. Turns from the length, current from the cross-section area into length is a volume. And whatever the volume, weight will be the same. Okay? Higher the volume, higher the weight, lower the volume, lower the weight. And after that, give ordinary transformer weight and auto transformer weight and take ratio of both. So you will get that. Alright. Write it down and stop it.